So, Arshdeep, I would like to ask you that at IIT Mandi, do you have this IEEE SPS Society?
Not really. Actually, this some of this work that I'm going to present is being sponsored by this SPS Society. So
Okay,
I'm a member of that. I think it's been expired, but I was member of that for 3 years. So I just
okay,
put
okay,
this logo. Yeah,
okay, fine. Because
IPP.
even we got one project level, like one proposal accepted by SPS, and
Uh,
in like around I think July or August, we were planning to host SPS summer school.
that's nice.
So yeah, so you kindly join that time also because we
Yeah,
have got
sure,
huge
sure.
fund from SPS.
So in IIT
And,
Mandi or in general in India, so there is a speech society. I just forget the name. So
okay.
they organize every year this winter school of
Yeah,
speech
yeah,
and
winter and
language.
summer school. Two things are there. Yeah.
Yeah, yeah. So they organize every year since 10 to 15 years they are organizing.
Yeah. That is also focused on AI/ML only. We wrote a
That
project
focus
on
on,
that.
yeah, that okay. You're the summer school, right?
Yeah, the summer school is focused on AI/ML again.
Okay, okay. So in general, all applications, not particular to one.
Yeah, all applications. Yeah.
Okay, okay, nice, nice. Yeah, that's good.
We'll
Actually, that
update
should be
you.
there. Sure,
Yeah.
sure. So this summer or because of this corona and thing, it will go to
Maybe
winter.
it will go to winter now.
So
Maybe.
when okay, okay.
Actually, we got the approval. Everything was ready. Like at our end, we got the funds also, but
So
only the execution of the plan was remaining. But then this corona came, so
yeah,
everything has got
maybe
delayed.
yeah, you can wait and plan big instead
Yeah.
of in some hurry. So speakers will be from India only or international
No,
speakers?
no. We have from abroad as well. Yeah,
Okay.
international speakers are there,
Okay,
and
okay.
some WI speakers will also be there who are working in this domain. Because basically, it's on women in engineering also. Like a part of
Oh,
this
okay,
program
okay.
is focused to women, to empower women and all who are working in this area. So
Okay,
it's a
okay.
like
Yeah. Okay.
mixed thing.
Okay. So it's a
I
how
think
many
we
days
should
workshop?
start.
I think we should start now.
Okay, fine.
Uh-huh.
Yeah, people have joined.
Yeah.
So Arshdeep, I'll introduce you first to our attendees. Okay.
Okay. Yeah. Thank
Yeah.
you.
So good evening to one and all. I welcome you to IEEE AML Virtual Talk Series 2.0. And today we have with us Mr. Arshdeep. He's basically currently doing PhD at IIT Mandi, and his BTech he has pursued from Punjabi University Patiala in Electronics and Communication Engineering, and MTech again in ECE, and he is a gold medalist in MTech, and he has done his MTech from NITTTR at Punjab University. And I would like to state here that he has also worked at CSIO with Dr. Aparna and Dr. Sardana for 1 year as project fellow. And recently, he has also done his internship from Intel. Having so much experience in AI and ML, so I would like to invite Mr. Arshdeep for your talk now. So now over to you. You can start the
Okay.
session.
Okay. Thanks, Uma, for this introduction. So, can you hear me, participants?
You are
Hello.
Hear
audible.
you?
Yes, you can go ahead.
Yeah. So, my next question is how can you hear me? So this is what the sound is. So because your ears can sense the sound information that I'm speaking. So this is what I am going to talk on this sound thing today, and of course machine learning on this sound signal, right? So I'm Arshdeep Singh, as introduced by Anupama, and I'm from Manas Lab, School of Computing and Electrical Engineering in IIT Mandi. Uh, so okay, there is some issue in slide. The slides are not moving to next.
Arshdeep, you can share your screen again. Yeah, it
Okay,
might have got stuck. Yeah, try
so
sharing your screen again.
okay. Can you see now? Is it visible?
Yes, it is visible.
Lights are visible.
Okay, okay, nice, nice. So yeah, so I think you have heard the sound thing. So why means how can you hear me or listen to me because of the sound signal? So we are going to talk on the sound and the signal processing on the sound signal in respect of this machine learning field. Okay, so this is my campus in IIT Mandi. If you could see, it's a beautiful campus. They are in Command Valley. This is a south campus and this is north campus. So you can go from here by crossing this hill or by this road. So my particular area of research in PhD is the audio scene analysis. And I'm looking for pruning techniques for optimizing the neural network size. So I'm working with Padmanabhan Rajan. His area of interest is speech and audio processing, analysis of music, bioacoustics, word calls, means analysis of natural sounds, and machine learning, of course. And this guy Arnav Afsar, he works in diverse fields like medical image analysis, computer vision, audio as well. So let's start the presentation. So outline of today's talk is the first I will go with the introduction of this sound field, various research areas and applications. Then we will see the general machine learning approaches. And then I will share some of our contributions. And finally, I will conclude. So if we see information in everyday scene or scene you can consider as a physical environment. Here you can see a picture where you can see buildings, the cars, the vehicles, human beings. Okay, they might be speaking to each other or walking. So there is a lot of information in everyday scene. So the machine learning things, what they try to do is to utilize this information to make things automatic. Just wait. So make things automatic. So now there are various ways of this saving this information or processing this information. So one way might be the cameras. So cameras can record this scene and
Hello.
you can explore different areas using that vision based information. And other area is the microphones, so which can record the sounds which are present in everyday scenes. So we will, in this talk, we will focus on this microphone as a sensor and which store this audio information, sound information from the surrounding, and we'll see different applications and how things process in this sound area. So one of the research area in this audio field, sound field is, so I will use acoustics, audio and sound interchangeably. So three things mean same. So in acoustic scene classification, means acoustic means sound, scene you are looking for a physical environment, and classification means you want to categorize one particular physical environment from other. So given this audio information, say it is recorded using microphones. So simplest example is, let's you have a voice recorder in your phone, so you record audio information. So this is the signal that is recorded using microphone. So now in this area, the task is to categorize whether this small chunk of particular length is coming from which scene. Now here I show it's coming from car scene. So it may belong to street, home, park, and car. So the scene is defined by the application itself. So like you now are sitting in your private room, so that might be one of the scenes. So if you are recording that scene and try to categorize that your private room from the cafeteria or any other scene, so then that comes under this acoustic scene classification. So this is one of the areas that is recently being explored. And the next area is the sound event detections. So now you have the audio recordings from outside, from scene or environment. So if you are interested in finding different sound sources and also their start and end times, means at what point of time those events are happening. Like here I have shown, suppose you are in your home. So in home scene where you are sitting presently, so there can be car sounds from outside. You can walk and you can communicate with your family members or anybody, so those speech sounds. So this particular application, sound event detection, it targets to tell that at what interval of time, point of time, this car sound is being there. And similarly footsteps and other sound sources. So there can be multiple objects which can overlap, like you can see here, this car and speech, so they both can occur simultaneously. So the efficient system will tell you that this speech sound start from here, even if there is an overlap with other set of sounds. And the third area is the sound tagging. So it's very closely related to this sound event detection. Now here we have again this audio recording. So now a task is to tell the number of sound sources or the category of sound sources. Now it doesn't contain any temporal information. So this can be considered as a sound event detection system, but with weak label. So here there is no temporal information uh, is there. So you can also consider it as a multi-level classification. So given this audio recording, you need to tell that how many the number of sources of sound are there. So these sources of sound mostly they are predefined according to the application. So now given this different areas, so I just exploring these three very popular and the recent areas. There can be other areas. So now where to utilize this such application? So means can it be utilized in real time? So that's the question. So you can think of any applications, any sort of application where, I mean, in which area you are working in. So but the idea is to use the sound information. If something produce sound, so can you use that information to design classification, tagging, or event detection system? So one of the areas that is being explored and the future scope is the context aware services. So your mobile phones should be such that they should automatically turn on silent mode whenever you enter a meeting, or if you are in party also, it should turn into on mode. So there should be intelligence in your mobile phone based on the context. So that's why it's a context aware. And services means you are the application of this. And even in Google self-driving car, if you see they are also utilizing this microphone or audio sensors to understand the surroundings. And the other application is the home monitoring. So in home monitoring, everybody knows Amazon Alexa, right? So Amazon Alexa, what it does is you can call Alexa and say play music or switch on lights. So this is what the speech processing or audio processing applications. So recently they are going to publish a home monitoring system where you can monitor the baby cry event. So you can monitor your, I mean, little ones remotely, and the events which can like the glass breaking, some the activities are happening, abnormal activities you can detect, and also in word species identification. So this kind of system can be utilized. And the other another application is the audio archive management. So now it's a scenario big data. Everybody is downloading or uploading the videos on YouTube. So is it possible to given the set of videos, so can it be such that the system automatically classify those videos, uh, those videos? Okay, so this system, if we use it, can given this video information and using audio, so it can categorize those audios or caption those videos automatically, and also some of the contents which is violent, and that can be informed to the security from the sound information. So this is how the audio archive management, automatic audio archive management, rather I say. And the not, last but not the least is the intelligent wearable devices. So in bioacoustic sensing, like we can consider our body as a scene. So there are different organs. So you can monitor this your body using this vibration or this sound information. So this is how we can use this sound area in different variety of real-time applications. And these are some of the applications. So you can think of any application and use this systems this in this audio processing field. So as compared to the speech and music processing fields, okay, which are well established. So example is the Siri. So or in any phones you can have I mean Spencer, which you can speak and they can type whatever text you have spoken. So it's very accurate system. So it's a well established field, speech and music processing field. So as compared to speech and music, this audio processing, it covers more range. Means speech particularly it's up to 4 kilohertz, and music application they have information up to 8 kilohertz. So but in audio in general, it's a application which cover the whole spectrum up to 20 kilohertz or beyond that, if you see the industrial sounds. And the similarity, if I have to say with respect to these field, is the acoustic properties. Like there are harmonics also, transients, and there can be noise like sounds as well. So multiple sources are present in surroundings, so they are mixing each other. So we can use similar acoustic features which are used in these fields, well established fields, like spectral features, log mel energy. Shortly I will introduce those. And you can use classification tools, CNNs, and that Vishwa has explained yesterday, or the future these lectures will take a look on those things. Gaussian mixture models, hidden Markov models, etc. Those classification models you can see. And what the difference, if let's see the difference. So in as in speech, it's a well established thing. So there's a well mathematical models for that. In this audio thing, there's no taxonomy of events. So very good example is if we compare the bus station scene in India versus the bus station scene in Europe, in Rome, say. So they you can get different kind of audio signatures from those. So you can't have a single category which generalize across all the world. It is dependent on the location. So there is no established taxonomy of events and scenes. And in this audio processing, in scene classification or this event detection, so the sources, there can be multiple sources, and they can be far away from the microphones, because it's a scene is a more you can say it's a big area, and speech is like you have a microphone near your mouth, and you can hear those sounds with noise cancellation and all those things. But in audio applications, so sources can be many and they can be far away. So SNR is very low as compared to speech kind of signals. And also there are many independent sources. So say there are 5 sound sources and they are mixing, and one microphone is recording that information. So while at the recording end, so those signals can meet in a constructive way or destructive way, so which can completely lose the structure of the signal. So you can lose, suppose a 50 hertz signal is coming, and again 50 hertz is coming, but at 180-degree phase difference. So you will get a single line at 0 hertz. So the whole all information can be lost with this multiple sources. And since it's a new field, people have started working in this field. So available data set for building the models as compared to speech and music data set, they are still a bottleneck. So in general, so am I audible, right? Any
You're audible.
Okay, cool, nice. Yeah. So in general, machine learning, so it's acronym for machine learning, ML. We have this audio information from microphone. So the first task is to extract features. So we can't process this audio signal directly because of memory issues. You can't process this raw signal directly. So you need and also for more interpretability, so we need some transformation on this audio, which project this audio signal into low dimension, more discriminative space. So we look for feature extraction methods, so which give us acoustic features. So now instead of processing this audio signal, we process this acoustic features using this machine learning algorithms. And these three tasks that I already explained. The classification is single level, tagging it's a multi-level, you can see, and this detection is the multi-level with this temporal information. So while training stage, what happened is, so given this acoustic features, the aim is to learn this acoustic model in such a way that your predicted output, that is y hat, and the true output is minimum. The loss between or difference between in simple sense, so it's minimum. So typically we use this loss function uh, uh, as a you can say the similarity or the mean square error, or there are different loss functions, so which depends upon this training algorithm which you are looking for. So and also it depends upon certain assumptions that the loss, which loss function you are choosing for. So the ultimate aim is to learn this model or parameters of this model by minimizing this loss function given this acoustic set of features. Now, while testing, once we have learned this model, acoustic model, and while testing we have a test audio, we again use that feature extraction thing, so remaining in the same space as we used in training strategy. So we extract the acoustic features, so then this it will give us the probabilities, so that we can post process on this, so which gives the indication. That's the evaluation stage. So so this is the general framework. Now let's talk on the acoustic features, so different acoustic features in this sound space. So given this audio information, the typical thing that is done is the windowing operation. So from windowing, I mean that, so given this audio information, say it's a 3 second long, so we will take small chunks. We will take small chunk, say 25 milliseconds or 30 milliseconds, and this windowing operation will extract that small chunks. So this is the meaning of windowing operation. So it will extract this the consecutive windows and process that small chunk. So given the windowing operations, why it is done? Because we assume that the signal remains stationary for this period of time, 20 to 40 milliseconds. So it depends on application as well. So it's a hyperparameter. So in speech, it's proved that the typically 30 millisecond window is an efficient way of computing the features. So given this after windowing, so segmenting this signal into small chunks, either the temporal features are being extracted, which are zero crossing rate, so how many times this signal is crossing the zero, and the autocorrelation means how these two segments are autocorrelated, and there's the statistical movements, first order, second order, means mean and variance, uh, or this is the in the temporal domain. In the Fourier domain, in the frequency domain, so Fourier transform can be applied, or wavelet transform, so to extract the spectral features. And people have also used the statistical features on the spectral, this windowing thing. So this was the traditional thing that was happening in temporal and spectral after this windowing. The standard thing that is being done is the time frequency representation, because it is more discriminative to extract this time and frequency information both, rather independently processing. So let's extract this time frequency representation, and then you can do some image based features on it on this time frequency representation. So now let's take a look what this is the what is the this time frequency representation. So this is a audio signal, so you have applied this windowing operation. Now just concentrate on one window, This is the suppose first 25 milliseconds, and if and you are doing this Fourier transform. Like Fourier transform is the output of this Fourier transform is the contribution of different frequency components. So it will give a vector, so that we call as a spectrum. So it will give the contribution of each frequency component in this. Okay, and similarly you extract for the next this segment or frame. So when you stack this spectrum extracted at a different interval of time, so you will get this 2D matrix, not 2D but 3D matrix. So this the x-axis is the time information, so which indicates that for this segment you are getting this spectrum, and for this time you are getting this spectrum. When you concatenate this, you will get a spectrogram. So this 2D matrix, which have the each entry belongs to the energy of frequency component. That's why it's 3D matrix. So one axis is time, y-axis is frequency, and this z-axis, that the color that you are seeing, is the energy contribution of each frequency component. This way spectrogram is extracted, and so this is what the time frequency representation are. So it contains both time and frequency information. So further this given the spectrogram, then this spectrogram is further convolved with this MEL filters. So now this MEL filter is coming from the speech processing field. Since we as human being can sense the frequencies of lower band, typically up to 2 kilohertz, 3 kilohertz. So what this MEL filter does is it gives more resolution to lower frequencies. You can see here this the filter resolution is up to 4 kilohertz. There are more number of filters, means their width is lesser, and for higher frequency this width is more. So it means that you are providing more resolution to lower frequency components. So then another you will get this MFCC based representation after this convolution, spectrogram, and this filter bank. This filter bank is inspired from the speech model, the human models, vocal tract models. So MFCC features this MEL frequency of capstone coefficients, or the log MEL features. So they are nothing but the transformation on this spectrogram by convolving with this MEL filters and applying some more operations on this output. So this is typically that is being used in speech thing, and also this thing also applied in this audio scene classification, event detection, or the sound tagging as well. So let's understand this spectral feature. So what actually they represent is, so let's say this is the recorded signal, which I'm interested in finding its the linear combination or contribution of uh, A, B, and C signal in this given signal. So what I mean is, so I want this signal to be splitted into this A, B, C signals, and want to find how this A signal contribute to this signal, B signal contribute to this signal, and similarly C signal. So here, if you see this A signal, B signal, let's say it represent 100 hertz. So let's say this is one second chunk, so it has two this peaks, periodic peak. So I will say it's 100 hertz. With respect to B signal, A has a lesser frequency since only one peak is there. So you can say it's a 50 hertz signal, and this signal has 25 hertz. Again, half of that is A signal. So we are looking for different frequency component contribution in this signal. So mathematically, I can write it as signal is equal to D into R, where D will be this matrix A, B, and C. So here the columns of this D matrix are A, B, and C, and the contributions of each frequency component will be this tuple, this R1, R2, and R3, where R1 tell you the contribution of A in signal. So you can now motive to show this particular this framework, this signal is to DR, is to introduce you this D, which I will refer as dictionary. So now here this dictionary ABC is coming from this Fourier space. So if you see the Fourier atom, they look like this. They have different frequency components, and you are, for a given signal, if you take Fourier transform, you are actually doing this thing. You are computing this R corresponding to the signal. So instead of processing this signal, so now we'll process this R representation signal or features, spectral features signal. Okay, so this D is a dictionary which is predefined. So now other people, what they did is, so they also use feature learning. Since if you see here this D dictionary to find the representation, so D is a fixed dictionary, so it's a predefined dictionary, so it's not adapted to the application, or you can say it's a hand engineer features, because we have used this Fourier basis irrespective of the application, so we haven't adapted these features for our particular application. So people have explored the feature learning, so where the ML came into picture. So given this audio signal, as I already explained, this time frequency representation using this Fourier basis, we can compute. So people have used the ML to extract features from this input acoustic features using deep learning, where deep learning is machine learning came into picture. Sorry. And now it can be divided into supervised with the DNN and CNNs. So only difference is the architecture here, DNN in DNN and CNN. And in unsupervised framework, so some people have used bag of features, means clustering these features and come up with another set of representations. And some of them also explored the matrix factorization techniques, the non-negative metric factorization and its variants. So shortly I will just explain this technique, particular dictionary learning technique. So now, so far we have discussed that uh, the different applications of audio and the time frequency representation, which are handcrafted, this Fourier basis. And to overcome this, people have used this feature learning to extract high level features using this deep learning or matrix factorization techniques. So any doubts so far, participants? Hello, can you hear me?
Yeah, we are able to hear you.
Okay, so any doubts so far from participants?
Go ahead. No.
Okay, cool.
So you can
So
go ahead.
okay, sure. So I just want to clear one thing. Can you see my cursor? This red moving?
Yes,
Yes,
we are
sir.
able to see.
Okay, cool, nice.
Yes, sir.
Okay, this. So let's now. Okay, it got hanged. Okay, it's fine. So let's see one. Now I will explain this matrix factorization technique. One of the technique that we have proposed, we contributed. So just some nomenclature before proceeding further. So this is audio signal, again a reminder. So this is log mel spectrogram, or this acoustic features in this matrix form. So let's say this is x1. So the dimensionality or size of this matrix is d into n1. So where d is the dimensionality, so this y-axis. So you have d features. So each feature each feature corresponds to the energy of the frequency band, particular band. It's a d-dimensional signal, and there are n1 time frame, that segments that I have already discussed. So let's prepare data matrix X. Let's say I have m examples. So these are stacked all together. So which will give me this data matrix X, D into this much. Okay. So means I'm interested in finding the representation of this signal in a new space, in a high, in a more discriminative space. So that's why I'm just trying to build a data matrix to learn a dictionary, so which will be adapted to the application rather than using the Fourier atoms or dictionary. Okay, so yeah, so this is X data matrix, just keep in mind. And another thing is the convex combination. Let's see what it is. Let's say we have 2 points A and B in some d-dimensional vector space. So let's say I want to generate some C with this combination. So alpha into A, so alpha into this point plus 1 minus alpha into B. And here the constraint on alpha is 0, it belongs to 0 to 1. So can anybody, can you think of what will be this C? Will it be a single point? Will it be a set of points? And means what will be it be? Can anybody you can think of this? So what this C will be? So with this combination. So this combination is called convex combination. So you can think of for a while, for 10 to 15 seconds. Okay, it's a set of points, right? So yeah, you're right. It's a set of points because alpha is varying, but which set of points? So with respect to the C and B. Zero and one. Yeah, that's right. So so it will be a line segment which joins these 2 points. So the convex combination, if you take 2 points in d-dimensional vector space, and you take this convex combination. Why convex? Because I have a constraint on alpha, and this combination is called convex combination. It will generate a subset of points or set of points which will lie on this line, or many set of points. This is a convex combination, right? Just keep in mind. And let's take a look on convex hull. What is a convex hull? Say we have 10 points in this d-dimensional subspace. So from d-dimensional subspace, I mean, or vector space, I mean that the dimensionality of one is d. It's a vector of d dimension. Say we have this 9 points. So what will be a convex hull? So given a set S of points in d-dimensional vector space. So now we have a set of points, 9 set of points. So convex hull will be the smallest subset of these points. Out of 9, it will be some subset of points, say 2 and 3. So which will, whose convex combination, so set of those points convex combination will generate the whole set, this 9 points. Okay, now just spare 5 to 10 seconds to read this and think, can you come up with the set of points, subset of these points whose convex combination can generate this whole 9 points out of these 9 points? Okay, so anybody who can tell me you can tell me the number, means either 1, 2 can generate their convex combination can generate the whole 9 points, or maybe 1 and 4, or 1, 8, 9, 5, 6, 7, 8. Okay, and minus 1. That's not a right answer. I think n minus 1. That may be the higher upper limit of 8 is NC2. Okay, that might be, but I'm asking which set of points you means can we subset, like it's 1, 2. That's a general answer. So let's see. Somebody has mentioned some 5, 6, 7, 8. So if I join, suppose let's take me. Okay. So 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 somebody has said that it's a 1 and 6. So let's take 1 and 6 and their convex combination. So I will end up with this convex combination. But 2 I could not generate from this convex combination, right? So it's the wrong answer. So for 5, 6, 7, 8, somebody has mentioned, let's see. 5, 6, see the convex combination, 5, 6, 7, 8. Okay. So I will end up with all set of points which lies in this area. But again, I could not generate 9. Okay. So let's see if 1, 2, 7, 5, they can't generate because we still miss this 8. Let's see 1, 5. Okay. So they can't generate 9 because this convex combination of these will only generate this. So 3 and 5, interesting. 3 and 5, you will end up with this one line. Okay. So this is so the correct answer will be this 1, 2, 3, 4, and 5. So if you take these points and their convex combination, you can generate this whole space, this whole set of points that resides inside. So this is given a set of points, this is called the convex hull. So if you have a set of points which can approximate the boundary by taking their convex combination, okay, so that is called the convex hull. So for given this kind of data arrangement, okay, so the convex hull of this will be the boundary points like this, and the extreme point excluding this inner this parameter. Okay, so the motive to introduce this is, so we now we know convex combination, convex hull. So motive is to introduce because I am going to explain this dictionary learning framework, which is called archetype analysis. So just do not bother about the name. This now here the task, this what this dictionary learning framework does is, so it learns the atoms of dictionary. So these atoms of dictionary in Fourier, those are the sinusoidal atoms, right? So now we are trying to learn the atoms of dictionary such that they could model the convex hull of the data. So it's a purpose. There is a purpose of learning this. I will shortly explain, but let's see the procedure of doing this thing. So X, you know, right? This data matrix X1, X2, up to XN, XM, sorry. So we have M training examples. So we are interested in finding D and factorize this X is equal to D into A, where A will be the representation. So we want to use this A representation for classification, right? And the constraint now, and we are interested in finding the convex hull of the data. So now how it can be achieved? So if you put two constraints, one is this X is equal to DA, and D is the dictionary of archetypes, and the other constraint is the D should be is equal to X into V. Okay, so pictorially I will show you. So if you minimize this argument, this X data matrix into D into A, now here another we have constraint on D also, this D is equal to XB. Now the constraint on B and A is they should be the convex combination of, they should follow the convex combination or the convex set, they follow the convex set, which means that the sum of B should be 1, this L1 norm, simple, this v1 v2 v3 up to vd is equal to 1, and again the coefficients matrix A, it should also be 1. So this denotes the simplex. So it's mathematical terms, it denote the simplex of these set of points. So if you minimize this b and a in this way, so we can end up with this. So how can we end up with this? So this x is equal to dA means, so here the constraint on A is it should be a convex combination, right? So it means that the each data point should be generated by taking the convex combination of the dictionary atoms, and each dictionary atom should be generated by the convex combination of each data point. So these two constraints, let's see pictorially. So let's say these are the set of points. So each point you can consider as a segment in d-dimensional space. So here just to show it's in 2D. Just let's assume they are in 2D. So x and y, this space. So let's say this point will represent the frequency, this time frequency features uh, corresponding to that particular point of time that I mentioned already, right? I just want to remind you again. Let's see. So straight. So so each point is this column. Each point is this column and projected in 2D, right? So it means each point represent the time information, and the space is the frequency space. Okay, so if means we are interested in finding the boundary point of now with those constraints. So there are two constraints. So x and y, what they are representing is it's nothing. It's a means you have a d-dimensional signal. So just to visualize the information, you have projected into the 2D. So in d-dimensional, you can say they are the dimensions. Each dimension represents the frequencies. Okay, the frequency information, and these are the points which are collected at different time 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 interval. In 2D, it's just a projection, so we have projected those uh, some space where they are following the same thing. Convex hull, yeah, yes. So that's we are interested in finding D, such that that could that could approximate the convex hull of the data. So that can be achieved with this kind of dictionary learning framework. So you can do this thing with the deep neural networks as well. The only thing is you need to change the optimization function while learning the dictionary. Okay, so here dictionary D will represent the filters in CNN or DNN. So if we so with that two constraint, I again want to emphasize. So one constraint is this point should be, if suppose I have let's say what's the pointer. Okay, so this is one of the dictionary atom, and say this is the another set, and these are another set. So first constraint that is the x is equal to dA, and a is a convex combination. So given this d set of points, you could generate the whole data point with their convex combination, right? And the another constraint is that d is equal to xv. So you could generate this point by the convex combination of data points. Say this means these are the two constraints, so that will lead to identify this boundary points. Okay, so now the number of atoms while learning, that is the controllable parameter. So when I choose one as a archetype atom, so archetype here the dictionary atom, so it can be considered as that one of the Fourier bases, or now in this case it's not Fourier, but it's atom in this dictionary D. So you will end up with this mean of the whole data, because if you drive this mathematically drive this problem, so you will end up with the mean of the all data points is the optimal solution which can represent all data points. And if you increase the number of archetypes too, so this is how it looks like. So now means this is the optimal solution. So we can't always find the exact solution. So this is the optimal solution. So means given only two number of archetypes or atoms, so you can approximate this whole data if you have chosen these two stars, these two archetypes. And again, three, you can see this, it will form a triangle, right? This way. Okay, so their convex combination. So you can approximate these many points. And again with four, you can see, okay, so it will cover this boundary. So as you increase the number of archetypes, So you will end up with the exact thing. So now it depends upon the computation complexity. So as you increasing the number of archetypes, so you are also increasing the complexity in computation, right? So what you will ultimately, our aim is to show that this with this procedure you can approximate the convex hull of the data, right? So now why I'm interested in this convex hull of the data or the boundary of the data. So let's say, let's take two examples, two scene examples. So scene means physical environment. Let's say one scene as home scene, means you are at your home, and another scene is the classroom, right? So in home scene, people will be speaking, so the speech signals will be there, and in classroom also the teacher is teaching, so human sounds, speech signals are also there. So it's a common pattern that is there in both the scenes, and we are interested in discriminating those scenes. And but in home scene, if you see the sounds of utensils, okay, and which is not very common event in home, right? In kitchen, you can say yeah, it's a common, but I'm saying you are sitting now in a meeting room, so utensil sounds are very rare sound. And in classroom, the rare sound may be the door opening, or you can say the higher energy or many footstep sounds or the desk moving. So those sounds are rare sounds. So if we see the distribution of these sounds which are common, so those resides, those can group together. So you can consider this uh, okay, so you can this consider this as a speech sounds, so which are clustering together because they have similar properties. And you can consider this the boundary points, the sounds which are rare, okay, which are occurring rarely, or you can say they have different characteristics. So now here the emphasis is to discriminate between two very similar classes. So we should look for the sounds which are rarely occurring and which are more discriminative, so we can't ignore those sounds. So that's why we are interested in finding a dictionary, so which can represent the boundary point, the rare events, you can say. And the common behavior can be captured using the Gaussian mixer models, or this using this expectation minimization algorithm. So this kind of things. Prototype, yeah. So prototype I'm referring as the common cluster points which represent common behavior. So these are the mean, means if you have more than 30 samples, so if you take the mean of those data points, that is called expectation. So it is the sample mean. It means these are computed using Gaussian mixed models. So overall, yeah, it's a clustering. It's a clustering at the level of finding the prototypes. But for finding the archetypes, you are using that machine learning framework that I already explained. This using archetype analysis. Okay. So means prototype, generally we refer to the one point that represents, that can represent the average behavior of some common things. And archetypes, these are actually the similar things, but the notation wise, or the person who have first proposed this, they have used this archetypes as a term. So just to discriminate between these two things. So and this archetype and prototypes are they have different names. So what we the final this feature representation framework is, it's a feature learning framework, rather I would say, using machine learning. So for each sound class, say office, so we have this audios, we have generated this time frequency representations. Then given this set of training examples, we come up with this set of archetypes. So this red one is the prototypes, and the star one, blue one are the archetypes. So we come up with these set of patterns that can represent the whole set of atoms, with means instead of using 1,000 1 lakh points, you are now
English
having only
60 views
120 or
like
130 points
43 view.
that can represent the whole space or whole set of that signal. And similarly, we perform this analysis independently for beach sounds. So here, just to discriminate this star with the green color. So then a global dictionary is built by concatenating all atoms. Now the global dictionary represent the whole space of different categories, okay, with their representatives or atoms in the dictionary. So this is the training stage, right? So while testing, what is done is, so given this audio signal, again for a test audio, you generate this time frequency space acoustic features, and then you project on this dictionary D. This D is same as this, and you find this simplex projections by this thing. Now here D is not learned, it's a fixed. So, and you will end up now here. Now one thing I just want to say is, so the first few atoms, they are following this office, right? So those atoms belongs to office. So now since this test example is coming from office scene, so the projections will be higher, or contribution of this office atoms in the dictionary, so that will be higher. Okay, so this, that's why this is higher here. And for each class, since they are dissimilar classes, so they have lower this contribution. Similarly, there are other classes in between as well. Okay, so this is how this representations they now look like. So this now this up to this, there are atoms which are learned using tram signal. Okay, so that's why tram signal is higher for this for up to this number of points. So x-axis represent the total number of atoms corresponding to all the classes. Okay, so and there are around 120 atoms which correspond to tram. And again, for library classes, it was the atoms were here, right? So some 120 atoms which are learned using library class, so they are higher for library. These are for test examples, and for which you can see this is. So you can discriminate, means visually you can see the difference. So for classifier, it will be easier to discriminate between them. So here emphasis is so in machine learning. So whatever aim is to find a discriminative space, or rather I would say the space where which can give you some interpretability of features. And so with this kind of thing, so you will get more discriminative thing, and there, there's no need to put more efforts in classification. Okay, so and the I mean this is proposed in one of the papers, so you can refer to that. So we show that this performance using this time frequency representations is lesser than this kind of representation if you further process this. Okay, this is where machine learning is coming into picture. So now so this is the machine learning where you can learn from the time frequency features itself. But there is a problem with time frequency space um, as well. So let's see that problem. So now because we are using the time frequency features with the fixed dictionary Fourier atom, then we are further processing the another dictionary framework to learn more interpretable and discriminative features. But let's see the problem with the Fourier basis. So let's say this is a signal. Okay, so now you can see the transient are occurring here around 200. This is the zoomed version of this thing. There is a small change. Okay, it's periodically varying, but there is a small change. And here you can see here at around 800. So this is again a small change. Small change. Now let's see how this Fourier basis using this Fourier transformation time frequency representation they look like. So with if you take the Fourier basis transformation, the time frequency representation, that will look like this, corresponding to that signal, right? There are around 200. There is an impulse, sudden change. So corresponding to impulse, the Fourier transform will be flat. If x this y-axis is x-axis is f frequency, so you will get up this kind of this is a flat line. So means all frequencies will get activated. That's why there is a straight line. But you can see also this, the change is also here, detected here. So now why it is not detecting the transient, this Fourier sudden change? And so the problem with this Fourier basis is, if you see the time frequency basis atoms, so they have the problem of providing a resolution, good resolution in both time and frequency. So either you can have good resolution in time with the window of larger length, and then you will lose resolution in frequency. Okay, now it comes from the uncertainty principle. So so this time and sorry, this the frequency. If you see the width in time and frequency, it is constant, and it is constant. Okay, so now this problem can be solved if you have the bases or the atoms which are wavelet. Okay, I am sure you have heard about wavelet transform. So wavelet, what they have is different resolution in time. Now here you can see the width in time, and time is different for both cases, u and u naught, you can see. So with this larger width you have less resolution in frequency, you can see here. And for this particular, yes. Okay, so for this resolution, so you will have the higher resolution in frequency. So with wavelet thing, you can cope up this problem, and the representation that you get is like this. Okay, can you see the difference? So you can means easily detect this transient using wavelet transform as compared to the Fourier thing, because this means there is a difference at sounds which are occurring at 100 and this 200. Okay, so this is where this wavelet can be used. So what the problem with wavelet is, still you need to decide the wavelet, which kind of wavelet you have to use. Like here, this is a Morlet wavelet. You need to control the scale coefficients beforehand. So the alternate problem, or the machine learning where we can utilize, is the learning this basis. Okay, so where the machine learning came into picture in second. So before we have explained in high level discriminative feature representation. Now we can use this convolution neural networks, so which are standard in the vision based applications. So in vision based application, you can see the LexNet and all those networks since 2012. So they have they have a standard now. So ImageNet, they have a classification of more than 98% or 95%. So what they represent is they learn the feature itself from the raw data. So like you can see here, different layers can represent the edge blob. Okay, so texture information, or the higher layer, they represent the higher information. So this is where the machine learning came into picture, in learning this the Fourier, the the bases, which are an alternate option to Fourier and the wavelet basis. Okay, so so one of the networks that is in audio space is the SoundNet, so which is learned using this audio information using transfer learning. I will not go in detail of this. So I want to show you the filters that is being learned by this. If you see the filters which are learned from the data, raw data itself. Now here the input is the raw waveform, right? So it's not the acoustic features and all those things. So the filters learned by the very first layer, they represent this the different scale information automatically. So there's no need to set the scale or the kind of wavelet, mother wavelet that you're looking for. So only thing is to control the number of the layers, the number of the filters. So that can be, that's a hyperparameter designing parameter. So you can end up with this kind of filters which can be varying very fastly. Okay, or the events which are periodic, like the somebody's singing music. Okay, singing. So it's a slow pace varying signal. Somebody can speak or sing at higher frequency, so this can represent that information. And if there are transients, so if you can see the characteristics of this signal. Okay, So unstructured signal can be captured while learning. So this is how the frequency response of the different layers can look like. So they represent the different frequency information as well, the learned filters. So this represent the lower frequency up to say 4 hertz. This represent the band from this up to 15 kilohertz, right? So if I have an input audio signal, say this is the time information, and this is some event, baby cry event is happening at up to this point of interval. Say for first second it is happening here. So the feature maps or the output of the first the layer of this the network that I told you, the sound net. So that looks like this. So only few filters here. X-axis is the filter means feature map index. So this index indicate that the filters which correspond to this ninth filter is highly activated as compared to other filters for this particular sound. Okay, and this is the feature map for another for more deeper layers. As we shift this signal, so this contribution is also shifted. Okay, so now here I just want to conclude my presentation. So here motive second phase of last few slides to show that you can use machine learning to learn dictionary from the raw audio itself. Okay, so this will cope up the problem of Fourier basis, and it will be more adaptive to application, right? So, in conclusion, I would say we have covered this audio space with various interesting application and real-time applications. So you can think of applications on your own with the sensing element as a microphone, or you can use even a vibration thing like Mr. Devender is nowadays I think using so to record the data, or the earthquake warning system like they use that sensors to capture those vibrations and use this the literature in this particular field to represent your signal related to your particular application. And we have seen that the ML can be used in feature representation in an end-to-end fashion to learn those Fourier bases. And also you can use this ML in computing high level, more discriminative features. So it will be an alternate to the dictionary learning frameworks. Okay. So yeah, so so I will just stop here. And the some of the useful conferences that you can see for this literature is the ICASP it's a conference, and these are the workshops. So which particularly talk on which particularly give literature of the scenes, event classification, sound tagging, and this VSAP this is being organized in India. It's been started by ISC people and the people from IIT Madras. So every year it happens in India. Focus on this audio kind of application. And if you are interested in speech kind of application, the interspeech is the best thing that is there in the world. So in 2018, it's been organized in India, in Hyderabad. So this is some of the work that is being contributed by my team in this acoustic scene classification. So pruning I haven't explained here. So pruning means to reduce some of the redundancy in the networks. So with Arnav and this Padmanavan sir. So this is the work. And one more guy I would introduce is the Anshul Thakur. So he works in bioacoustic classification. So species classification. So he has submitted his PhD, and now he's doctor now. So means if you are interested in bioacoustics, so you can also look some of the papers of this guy. So these are some of the reference, and this is the contact information. Okay, so I would say thanks to student branch ACSIR CSIO and the organizer team. Thank you very much, audience. And if you have any questions, you can you can proceed with. Thanks.
Thank you, Arshdeep, sir. And now the session is open for questions. So if there is any query from any of the attendees, the speaker can take up now. Uh, Arshdeep, sir, there is one question from Pooja Serene in the chat box. So see if you can take up this question.
Mostly it was about slides. Okay. Sound data and okay, if apps we use. Yeah, yes, it's true. Means you can use sound data for that e-commerce and all those something like means Apple typically use Siri app to record your recordings as well. So to design more robust systems. Okay, and Shailesh has asked when there is a less spectral difference in two classes, can the algorithm work? Yeah, it's a tricky question and means uh, so when there is a overlap between two classes, so if there exist a events which are rare and if and they are more discriminative, so then this algo will work. So it's a difficult problem to separate out to mix which have very low temporal this spectral resolution, right? So uh, that means algo can work, but depends upon means how they are mixing or how close they are. Somebody is
Hers? Hello.
yes, I can hear.
Hello, Deep?
Yes, Devender.
Yes, Devan this side. Yes, Devan. I have couple of questions for you.
Sure.
The first is how the annotation was taken place in case of the footstep. As you were recording the sounds of footstep, so how you annotated? Suppose in between two footsteps, there is a noise. Okay, that means a background. So is the annotation was done, or you have just taken the complete time series signal for the complete footstep?
So it's a big problem annotation wise. Even this
Okay.
data is a big problem because because weak labeling people term as weak label because it's very difficult to have that population of people or research scholars to hear the sound and annotate them. So there will definitely be the human mistake in that. So if we are fortunate that we have that much data, so that system can be easily built. But the problem is this annotation. So maybe human error. Maybe if I am not in a mood of this annotation, so I can say yes, it is happening at third second, and you can see at 3.5 second, and somebody other can see at 4 seconds. So which has huge impact on the performance. So typically, while this the metric that is used for this accuracy or the for performance wise, so they have a 50% or some percentage of this threshold. So means you can be 50% right in saying that it is if it is exactly at suppose third second some event is happening, and if you are saying at 3.5 second or fourth second, it is fine means that is the metric performance metrics you can have threshold on that.
Okay.
So it's a problem
Okay.
means if you are means if you
Yes.
could come up
Okay,
with
I got it.
the if you come up with this data set, then you will be recognized.
Okay,
Yeah.
good. The second question is, what was the method behind choosing the window size? Like you said, 30 millisecond. So, is there any particular reason for choosing the window size? Means, have you seen the effect if you scale up the window size in case of taking 30 millisecond? If you are scaling up to 100 millisecond, so what are the changes in the output? Have you observed?
So regarding this, I would say this 30 millisecond it is coming from the speech field. So in speech field, they are models, mathematical models, like we speak with vocal tract, right? So it is observed that the signal remains stationary for 20 to 40 milliseconds when we speak. So from stationary, I mean that if you take a chunk of 30 millisecond, and if you again take chunk of 30 millisecond, so the statistical movements, they remain more or less same. So this 30 millisecond is coming from the speech processing field for if you are interested in this speech field. But for other fields, it's still a hyperparameter, and it depends
Okay.
upon your signal. So either you can, what you can do is you can have some set of data, so you can observe the means how, for how many this window length it is remaining stationary. So that can be done, means. So for this
Okay.
work, so we haven't this consider this thing, because actually we are interested in something else.
Okay. Okay.
Yeah, yes.
Okay. Now my another question is there any effect of line frequency in acoustic signal processing?
Line, so it's very low frequency, I guess, right?
No, if in suppose in outdoor scenario, you are
Mm-hmm.
recording any signal, acoustic signal, and
Mm-hmm.
if there is a high tension line, then
Okay.
what will be the effect of the line frequency on your signal?
Okay, so ultimately in scenes, so we have suppose multiple recorders, so it is recording everything around the scene, right? So it can be line
Okay.
frequency, it can be the engine sound, it can be human sound. So then it gives you the culmination of all the signal that your microphone is. So the line frequency may be the features which are more discriminative to classify that particular scene from other scene, right? If you are suppose in outdoor or in park, uh, and
Mhm.
it's very subjective actually. So if
Okay.
means it's very subjective. So if you are interested in means in classifying one scene where this line frequency is always there, so then it's a
Okay.
useful information for you. It's not a noise. So this is the
Okay.
biggest difficulty in scene, so to
Mhm.
differentiate between noise and signal, because for one scene it can be noise, for other scene it can be signal.
Okay.
So yeah,
Okay.
so
My last question is suppose two signal happens at the same time. It is completely overlapped. Then how to
uh,
handle this situation?
you can't handle that, because if they are out
You
of
can't
phase,
handle.
so
Okay.
you if they are out of
Okay.
phase,
Okay.
they are out of phase, then you can't handle. Nothing is in
Okay.
control.
Okay.
So it's only thing
Okay.
that, I mean, that can be done is, so if you have prior information, you can have a setup of microphones, recording devices, in such a
Okay.
way that means the information is not coming out of phase.
Okay.
Okay, yeah.
Okay.
So that's
Okay.
that's
Thank you.
yes. So
Thank you.
in event detection, that's a big problem. But in scene, it's fine. It's because we are not
Okay.
interested in classifying the source. Yeah, yeah. Yes.
Mhm.
Hi
Okay.
Arshdeep.
Okay. Thank you.
Hello. Yeah.
Hi. First of all, it was a really nice presentation. So I
Thank
have
you.
a question regarding the framing part. So like
Mhm.
generally when we work with the spatiotemporal features, so we do the framing and we take the overlap between the frames so that we don't lose information, right? But when you're
Mhm.
working with the archetypal, that archetype model, so you are
Mhm.
basically discretizing the data like in time space or like in frequency space, right? So you might be
No, no,
losing information. Yeah.
no. Means I am using archetype on the top of this time frequency features where there is a overlap. So I have still
There is a
using
overlap.
this. These, yeah, yes. Still there is a log mel feature similarly extracted using that overlapping and non-overlapping thing.
Mm-hmm.
So then means for each frame we are representing as a point in space. So
Okay.
that is, yeah. So, yes.
Okay. And like the other question was like when you shown us the graph like where there were different colors, right? So how do you actually segregated those colors separately? Like shouldn't there be a mixture of all these colors if they were like generated from a Mel spectrogram?
Yeah, I would show. Yes, let me go to that slide. Yeah, so you're talking about this yellow color, green color, right?
Yeah. This one.
So this is a you can say the frames, time frames with the frequency information in tram, right? in
Mhm.
Europe there is a tram. So tram means it's a kind of train, so
Mhm.
bus or closed bus. So if you have this data and you cluster this data using Gaussian mixed model, you come up
Mhm.
with 4 clusters, right?
Okay.
So here I can assume that this cluster represents the speech sounds, because there
Mhm.
are people in the tram. And this cluster which is far away from here, it can be the engine sound.
Mhm.
Okay. And this can be means footsteps or door closing or those things.
Mhm.
So this is means this cluster represent the different sources. Because
Mhm.
why I'm saying it's a hypothesis. Why I'm saying, because the speech sound, since they are coming from a human thing. Okay, so they
Yeah.
cluster, they should cluster. Okay.
Yeah.
But still say just a hypothesis in this ideally,
Mhm.
because there will be variability of speech sound as well, from male to female, right? Human to
Mhm.
human. But that variability won't be that much, so they
Yeah.
should cluster together. That's
Mhm.
why this yellow means you can assume as a human. Now here in library, so this yellow indicates something different. It may
Yeah.
be the book sound. Okay. And
Mhm.
this can be the common, like some ACs on there, so that AC sound, air
Mhm.
conditioning sound, right? So
Okay.
that can be considered. Yeah.
Okay. And I have like one last question. It is regarding like mel frequency Spectral coefficients. Like whenever we use MFCC, so there's always a question about like how many coefficients should we consider for a particular application. So how you like some people use like 13, some people go for 40.
Uh-huh.
So how do you actually
Uh-huh.
deal with that thing with your
Yeah. So
research?
if you see this MFCC feature, so if you
Mhm.
are really interested in the information which
Yeah.
is in the lower frequency bands, right?
Mhm.
So then you can go for first 13 coefficients, because
Okay.
if you see the whole mathematics behind this, or filter bank, so first 13 filter bank, they are up to I think 4 kilohertz or 6 kilohertz,
Mm-hmm.
right? And if your application is demanding for higher frequencies, means there are more frequencies, so then you
Yeah.
should use the whole band of frequencies. It's
Okay.
like a, you can say it's a compression thing, or means you are looking for less low dimensionality signal with more information,
Mm-hmm.
ignoring the redundant information. But for that you need the domain information as well.
Yeah. Okay. Thank you.
Yeah, well,
So any more queries?
Hello. Hello,
hello.
Ash. I want
Yeah.
to ask if there are some open source sound data set available to work with.
Yeah, yeah, yeah. I will share this. Forget to see that. I will open a website so you can all
Yeah,
open.
thank you.
So one community that is interested in this kind of application and started this particular applications is the DCASE. So this is acronym for detection and classification of acoustic scene and events. So
Okay.
every year what they do is they organize a challenge, uh,
Mhm.
and like in this 2016, if I can, you see this browser?
Gray screen is showing up. Gray screen is showing
You
up.
need to, Arshdeep, you need to
I will
switch the
share.
application.
Okay, I need to stop sharing and then
No, no,
again
no,
share
no.
with
Just
this.
click on share content or switch. Okay, you can do that.
Okay, Chrome. Yeah, this is.
Because my area is text analytics, and
Can you see
this
now?
seems interesting.
Yes, yes.
Yeah, yeah,
Okay.
yeah.
So if you see this D case, so this is detection and classification of acoustic scene and events. So since 2013 and continuing from 2016 to 20, every year they organize this challenge, right? So there is a workshop also. You can submit your paper to workshop. There is a challenge. So this challenge comprises of these different tasks, right? Acoustic scene classification we have seen, the sound event localization we have seen. Okay, and this is similar thing. This is urban sound, means in this urban areas, And also one of the area that is being introduced in this year challenge is the anomaly detection in machines. That is more related to electrical people, but now we can also, this electronics and other computer science people with machine learning thing can participate in that. Means you can explore this, means anomalous sounds. So this for each task, if you click on this task, there is a abundant of data. Okay, so there's a description, rules are there, you can download this data set. So this is the website that you can follow. There are different tasks as well, and you can download the data for your own application as well. So if you are interested in coming up with a model like CNNs in computer vision, so you can download plenty of data from this website and use this data set to design for your own application, right? Yeah. Hello. Yeah, that's it.
Any more queries from the participants?
So if there are no queries, so let's thank our speaker. Thank you, Arshdeep, for wonderful talk.
Yeah, thanks.
And
Thanks,
now,
Matt.
to make it more memorable, let's have a group picture with the speaker. So I request everyone to turn on your camera, and we can have a group picture. Yeah, I request everyone to make it memorable for the speaker.
Okay. So can you see me?
Not yet.
You can click on stop sharing now. If
Yeah, you can click on stop sharing.
yeah.
Yeah, now it's fine.
Yeah. So I request other attendees also to turn on their cameras.
It's on, right? Can you show me?
I'm still not able to see you, Ashdeep.
Still, oh my.
Yeah, turn on your camera.
Okay.
Vinod, I'm also not able to see you. Can you check up?
So I have started this thing, but I cannot. Still not visible.
Still not visible to me.
You can use your mobile also.
Yeah, Ashdeep, you log in through your mobile. Not
Oh,
an
that's
issue.
Yes.
okay.
Yeah, we'll wait for a minute.
Sure, sure. Thank you.
Yeah. That's good. Today we have more participants in the picture.
I hope I haven't bored with math and all.
Okay.
Um,
Salesh sir, could you again turn off and turn on your camera? You are getting a blurred image.
not refresh. Just wait.
Yeah, waiting for the speaker to join.
Sorry, it's just taking time.
Okay.
So can I connect parallelly with phone as well with the same account? I think.
Yes,
Yeah,
yes,
yes.
yes.
Yes, yes.
Click on the link.
Just click on the link and just turn on your camera.
Showing some.
So we hope you all enjoyed the session.
saying some cannot refresh. Come on. This is not the way. Some problem is there. Let me enter the meeting code and see. It's actually showing some unable to join. I don't know why.
Uh, okay, there might be some technical issue then. In the mobile as well?
Okay.
Yeah, in the mobile actually. Let me see again. It's a report problem, some connection issues or.
Okay, okay.
Number
It's fine.
go
It's
ahead.
fine.
So,
On my behalf, Devender, you can. It's fine. It's fine. It's okay.
Okay,
So,
tomorrow.
no,
yeah,
it's fine.
tomorrow then we'll have. Okay. Okay, thank you all.
Am I
Thank you.
visible
See
now?
you tomorrow. Stay safe and stay healthy. Okay. Bye.
Okay,
Thank you.
thank you. Thank you,
Okay.
everyone.
Thank you.
Okay.
Okay.
Thank
Bye
you. See you tomorrow.
bye. Okay. Bye bye.
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 Bye bye.